might not be morning your time, but it is mine. Okay, so the question today that you're solving is find if path exists in graph. So it says there is a bidirectional graph with n vertices where each vertex is labeled from 0 to n minus 1 inclusive. The edges in the graph are represented as 2D integer arrays where each edges I is equal to u comma v denotes a bidirectional edge between vertex and vertex. So vertex u and vertex I. Every vertex pair is connected by at most one edge. No vertex has an edge to itself. You want to determine if there is a valid path that exists from the vertex source to the vertex destination. And even given edges and the integers n, source and destination, return true if there is a valid path from source to destination or false otherwise. So in example 1, we see that this is true because the edges are 0, 1, 1, 2, 2, 0, and n is equal to 3, and destination is equal to 2. And this is true because there are two paths. So integers are the number of numbers that we have here. Said number of numbers, sorry. Integers are the numbers that we have in here, and edges are the edges we have. So 0, 1, 1, 2, 2, 0. And then the source is starting from 0 and our destination is 2. So we can see that we actually have a way to get from 0, which is the source, to 2 directly. And we also see that we have a way to get from 0 to 2 through 1. So 0, 1, 2. So that's why we have true here. Now over here, n is equal to 6. So we have 6 integers and we have multiple edges over here. Our source is 0 and our destination is 5. As you can see, there's absolutely no way that we can get to 5 because there's nothing connecting it. If it was 3 or 4, there would be a way. But over here, 0 connects to 1, 1 connects to 0, 0 connects to 2, but it doesn't, 0 cannot connect directly to 5. So there's nothing linking it together. Maybe if you had something connecting it here. So in this type of approach, I would use depth first search, and I would use depth first search using a stack, which is an iterative approach. So the first thing is to set a base case. You can also use recursion to solve this type of question. So if source is equal to the destination, then we have our answer, which is true, because that means we don't have to spend time running an algorithm or So now I'm going to be using a dictionary to store the values. Okay, I'm going to be using a dictionary to store the values. So graph is equal to, I'm going to create a default dictionary for that, and what it's going to do is that it's going to take in the list. It's going to be a list format. It's not going to take in the list, but it's going to be a list format. And I'm going to say for u comma v in edges. So we have vertices in here in our graph. I'm going to be saying that I'm going to be appending it to each other. So I'm going to say graph. I said to each other. So what I'm going to do is I'm going to say that for each vertex, or for each, let me see, where edge is this unit, for each vertex, right, I'm going to be appending it to the graph. So graph of u, right, which is going to be a key. I'm going to append vertex v, and so I'm also going to say graph of v, I'm going to append vertex u, and so then I'm going to be having a set, right, which I'm going to be using to keep track of duplicates. I don't want to have any duplicates in there, so I'm going to say scene is equal to a set, like I said before. And what is going to happen is I'm going to say scene dot add, I'm going to add a source. So we're going to add the source right, the value which everything originates from, and then we are going to put that in a stack. So we're going to put that in a stack to work on depth first search. Now we're going to be saying that while we have our stack, what we want to do is we want to pop from that stack. So if you remember, the stacks is LIFO, so last in first out, or first in last out, and we're going to be saying our node is equal to stack dot pop. So we're going to be removing that last value in there, and we're going to be saying if node is equal to our destination. So if we found one where the node is equal to our destination, which is part of the base cases for it will be true or false, we're going to return true. But if we have neighboring for the neighboring nodes in sorry, let me move forward a bit, and I misspelled true over here. So I'm also going to be saying that for the neighboring nodes in our sets, right? So neighbor node neighbor, I just put it like that, node, or maybe node A in, actually no, in graph node. So I want to find out like how many things do I have that are in the same graph as this. So for neighboring nodes in graph node, I'm going to say if node neigh is not in scene, I'm going to add it there. So scene dot add node neigh, and I'm going to append it to my stack. Then if this continually runs and it there's never a situation where the node is equal to the destination, then we know that this is false. So let's look back and retrace our steps and study this. So if source is equal to our destination, which is our base case, which is the entire goal of this algorithm, then we're going to return true. Then if this is not the case, we're going to initialize a graph, which is going to be a default dictionary, right? And we're going to be appending, so the key is going to be the vertex, right? And it's going to be appended to another vertex, which is going to be the value. And so, oh wait, am I correct? You know what? How about this? Let's run this. Okay. Method is not subscribable. Review the append. Sorry, give me 1 minute. Do I have the edges? And this should work. Type error. Oh, okay. Sorry. My mistake. I kept that in an array brackets. Okay. So what I'm going to do now, I'm actually going to print out what is inside our graph, so we see it. Print graph. Okay, so we see that we have, this is super smart by the way. We see that we have our node, right? Let's say we have a node 0, Okay, so we have a vertex 0, which is basically our source node. So we're going to be appending the vertexes that are attached to it. So like 1 and 2, vertex 1 we have 0 and 2, and vertex 2 we have 1 and 0. Let's look at our case for the second one. So sorry, I need to drink water. So for this one we have if you look at what prints out, for 0 we have 1 and 2. For 1 we have 0. Okay, it's attached to it, and we can only get to 2 through that 0. So for 2 we have 0. For 3 we have 5 and 4, because you see that from 2 edge points you can attach to it. From 5 we have 3 and 4, and from 4 we have 3 and 5. And so if you keep on going, right, that's what our graph says, then we now have a set which is seen. Okay, so it keeps track of the source node, and then it appends that source node into a stack. So we're not going to say that while we have a stack, while we have our source node inside that stack, we're going to be saying that we're going to be popping it and making that our node. And if that node is equal to our destination, then we are true. What's going to happen here is we're now going to use the iterative approach for breadth first search. So we already started this process here, but for neighboring nodes inside the graph. Okay, so one thing we can also do too, let's print what is inside graph node to see exactly and explain this very well, because the goal is to understand, right? We don't just want to brush through it and not understand. And I'm going to comment this out since we already saw what graph is. Now let's see. So if we print out graph node, what is inside there? So we see that the graph node has our initial node 0, and it has 1 and 2. Now let's look at the other side. Okay, the graph node is 1, 2. Okay, so if node neighbors is not missing, so for each individual one, if it's not already inside this asset, okay, if it's not already inside this asset, then we are going to add it. We're going to append it to our stack too, and then we're going to do the same process to check whether there's a connection between the source and the destination. But in this scenario, we have 1, 2, 0, 0. Okay, we appended it into assets, but then the destination is 5, so it can never reach there. That's why we now return false. So thank you so much for watching. I'm going to put the time complexity for this algorithm in the chat, in the description. Yes, so thank you. God bless you. Have a good day, and thank you.